So good morning. My name is Mohammed Abdal, and I work as a research scientist at Software AG. Software AG is global software company located in Germany and offers solutions to drive digital transformations. And also our portfolio includes solutions to connect, collect, and analyze data from different sources. So this work is joint work between Technical University in Darmstadt and Software AG. And this work is done by Benjamin Helperschut, Christian Hammacher, Eduardo Dos Reis, myself, and Karsten Pech. So, and it's funded by Federal Ministry of Education and Research. And today I would like to introduce our vision, which is differentiable machine learning, or DiffML, which is to develop end-to-end differentiable machine learning pipelines. What is differentiable, and why we need to turn data engineering tasks into differentiable programs? The idea here in traditional way of doing machine learning, like the figure here, data scientists have to spend lots of time, maybe 40 or 60 of their time, trying to impute values, to detect errors, to correct such errors, to augment data, to do wrangling, feature selection. All of these features, all of these techniques take lots of time. And according to our recent surveys, this also, as you can see on the figure here, represents the least enjoyable part of data science, which is cleaning and organizing data. Taking also into consideration that this kind of tools or pipelines developed in one project cannot be sometimes reused in the next project, since we are talking about different data or different business problems. So what is our vision? Our vision is to replace the state-of-the-art or the traditional machine learning pipelines, even if they use automated data cleaning tools. So in this word cloud, from one of our previous papers, we collected most of the state-of-the-art automated techniques to perform data cleaning. If you will be using one of them, they could be beneficial, but you don't know exactly what will be their impact on the end-to-end performance. You need also to make some kind of feature selection, either manually or using one of the automated tools. So our vision is to replace this with differentiable pipelines, where we jointly train pipeline steps and model for optimal accuracy. So we turn data cleaning into differentiable program. Feature selection should be translated into a differentiable program, and we can use then backpropagation in order to optimize the entire pipeline and train it end-to-end. In this way, there's no need to choose the methods for each step, since in data cleaning we have plenty of steps, and in traditional way we have to select the most suitable one. But with differentiable machine learning pipelines, there is no need actually to select, since it is done automatically. So what are the challenges that we are facing? The first one is learning everything is non-trivial, or the idea of turning the different methods in machine learning pipelines into differentiable programs is sometimes not easy to be done, and sometimes also increase time, training time. And the idea of selecting between different alternatives of the data engineering steps is non-differentiable by nature. So we need to find a solution to this problem, and our solution in this problem is mixtures. So DiffML implements mixtures of pipeline alternatives by assigning weights to different alternatives, and enables the optimizer to learn these weights, and by this way we can identify or we can select between the different alternatives, or even make kind of combination between these alternatives. To prove the effectiveness of DiffML, we implemented 3 different use cases, which are different data engineering steps, including learned data cleaning, learned data selection, and learned feature selection. We will go briefly through each of these use cases, and starting by data cleaning. The idea here is to replace the traditional machine learning pipeline where, for example, if we have like missing value in a data record, the simplest way is to use KNN imputer to find the value of this null, and then we can train a model. But with differentiable pipeline, we can also implement some alternatives to KNN and use a mixture of cleaning alternatives by assigning weights to each of these alternatives, and allow the model to learn this weights. And by this way, we can have several opportunities. First one, for example, can be that lambda 1, which is for the first cleaning tool, equal to 0, and lambda 2 is 1. And in this case, the problem will be reduced to only using fixed mean imputation. Or sometimes we can have kind of combination between these alternatives if we lambda 1 equal to lambda 2. So in this way, we can learn data engineering steps jointly with the downstream task, and we can enable or allow of mixture of alternatives which can improve the prediction accuracy. To evaluate this work, we used 3 tabular data sets with regression tasks, where 10% of the data has common type of errors. For example, Pike has missing values, Airbnb has typos, NASA has outliers, and we compared DiffML to, which is a solid horizontal line here, with dirty case where no repair is done, and the dirty data is directly used for training the models, and is represented here by the dashed line. And this bars represent different traditional data cleaning tools. For example, we have dpost as error detection with mean imputer for repair data. We have detector 82 with mean imputation. We have missing value detector with mean imputation, and dpost with machine learning imputation, and here we use KNN imputation, and so on. So the main findings that we found here is that the best data cleaning tools always depend on the data set and type of errors. So for example, here we can find that the traditional is that dpost with machine learning imputation works very well here for the Pike dataset, but in the Airbnb dataset, it doesn't work well. The best one is dpost and mean imputation. So the idea of manually trying to select the best tool is non-trivial and requires lots of time, while DiffML is able to find this automatically for you. So DiffML here for Pike already resulted in the best RMSE, since it gives more weight to the dpost ML imputation and missing value detector with ML imputation. So as you can see here, these are the weights given to these 2 techniques by DiffML, and thanks to these weights, DiffML were able to achieve the same performance like this best tools. And the same also applies in Airbnb and NASA. And NASA, we have something different where DiffML were able to make mixture of tools, or since the best technique here, which was missing value imputation, was with machine learning based imputation. So it achieves the least or the lowest root mean square error, but DiffML managed even to achieve smaller than this value, thanks to combining between different alternatives. So some baseline also can perform worse than the dirty data set, like the case here, for example. So this line represents the dirty data, and some traditional tools achieve higher RMSE than dirty data. And we can show that DiffML shows kind of consistency of the result in the 3 datasets, and mixtures sometimes outperform individual baselines. Let's switch to the second use case, which is learning dataset selection. And typically in machine learning, we use data which may come from different or multiple sources, like from different databases, different data lakes, from IT devices, from ERP or CRM systems. Or we may augment this data with freely available open data, for example, from Kaggle or OpenML. And the problem here is that this new data or this free data may has low label quality, or the label quality at least is not clear. And the addition of new data might not always improve the downstream machine learning performance. In this way, dataset selection is a problem that data scientists often need to deal with in machine learning projects. So let's see how the training process occur in DiffML in order to select the best dataset, and the same training procedure will also be applied in data cleaning and also in feature selection. So the idea here is that we learn both weights, lambda for the dataset selection and theta for the model or for the target model. And we learn this in a single pass, but we sample too many patches per pass and then update this parameter sequentially. So at the beginning, we sample one subset from one subset of the data, train the model, estimate the loss A, and then update the weights of the target model. In a subsequent step, we load the other data subset, and we estimate the loss through forward pass. But here we don't update the parameters of the target model. Instead, we only update in a third step the weights lambda corresponding to whether we will use subset A or subset B, depending on the comparison between loss A and loss B. To evaluate this performance, we also used some datasets Spike, NASA, and RPNP, and we compared DiffML to a default baseline, which is nothing more than MLP trained over the union of two subsets. So to carry out this experiments, we divided in each dataset into two subsets, and we performed kind of perturbation by injecting some kind of errors into one of these subsets, and we wanted to evaluate the ability of DiffML to select the other subset. And as you can see here, for different percentage of errors, DiffML achieves the lowest or the smallest RMSE in all datasets compared to the default situation. The third use case is about learned feature selection, and typically in datasets that we are dealing with, they have either correlated data, like in this example dataset of customer behavior and demographics. For example, total purchase amount and number of items purchased, they are very highly correlated. Or we may have informative attributes like distance from distribution center or the number of customer service calls. So they are not relevant at all to the target that we want to predict. So in this case, feature selection can achieve high significant, may have high significant impact on end-to-end performance, but actually it's not that trivial to implement. As a traditional way of doing it, either through filtering through correlation or we're using one of the wrapper methods, which incrementally train the machine learning pipelines in order to select the best subset of features, or dimensionality reduction techniques like PCA, or embedded methods, which exploit some of the characteristics of the models, like feature importance in decision trees. Yeah, but the problem is that each of these tools has some shortcomings. For example, filtering, they overlook informative attributes and only take care of the correlation. For wrapper and dimensionality reductions, you have to train multiple machine learning pipelines in order to find the best solution. And for embedded methods, they are only limited to a specific model classes. So our solution here is by using DiffML is to assign a learnable weight to each feature and then learn these weights as usual in order to find the best subset of features. For the evaluation of this use case, we used 6 datasets. On the right column include wide datasets, which they have plenty of features, and the left column, it has normal or the small data set which has less than 40 attributes. So the main finding here is that we compare DiffML with FAMED, which is a generalization of PCA, dimensionality reduction, and also we compare DiffML to no feature selection, and we make the comparison in terms of RMSE, and the horizontal axis represents training time. As you can see here in all figures, we found that FAMED, which is the dimensionality reduction approach, is very computationally costly, since it has to train lots of pipelines in order to find the best solution. That's why it is always located at the end of each figure. And DiffML achieves competitive predictive performance while incurring almost no overhead. If we compare DiffML to no feature selection, DiffML is very close in terms of training time, and always it achieves better performance, especially if we are talking about wide data sets. DiffML even sometimes work better than FAMED. So what are the next steps? The next steps in this vision work is to explore other steps. It's not only about data cleaning or feature selection. We may also try to turn data augmentation or any kind of data transformation into a differentiable programs. We may also develop multi-step machine learning pipelines. So in this paper, we turn it the data engineering steps individually, but we want to put them in one pipeline and try to train the machine learning pipeline end to end and check the performance. But here actually we could have some scalability issues, especially when we are talking about mixtures, different alternatives for data cleaning, for augmentation would lead to increase the training time exponentially. And the solutions to this problem is to perform some kind of pruning, so reducing the number of pipeline combinations, and also we should take care of ordering. So sometimes it's naive to know that data cleaning or error detection should be done before data repair. But if we have several data cleaning steps, so we need to define the order. And our idea here is to enumerate the alternative, or the simplest approach is to enumerate the alternative orders as part of the differentiable program. Another direction could be differentiable operators, which is instead of implementing mixtures of each data engineering steps, the idea here is to implement each step into a differentiable neural network. So for example, for data cleaning, instead of using KNN imputers or standard imputers, we can implement a neural network which is differentiable by nature and can be jointly optimized with a target predictor. So as a conclusion, in this work, we introduced our vision of differentiable machine learning pipelines based on the idea of mixtures, and we show through the experiments that our approach can optimize for downstream performance and can achieve competitive results compared to baselines. And we showed these results using three use cases, including data set selection, data cleaning, and feature selection. If you're interested, you can have a look at the paper in an archive. And that's all from my side. Thanks a lot for your time.